Hi, my name is Mitali Gupte, and this is Lab 5 for Physics 2211, Choose Your Own Adventure. So in this lab, I'll be focusing on observing an inelastic collision and how we might use observational data to estimate the coefficient of restitution between a dropped object and the surface. I'll use Tracker to observe the motion, then use GlowScript to construct a computational model in which we can test different values to align the computational model with observed data. So first I'll be taking a video of me dropping an object and observe that motion in Tracker. Then extract the data and construct a computational model in which I'll compare that with the observed model. So a bit of background information. I'll be using Newton's second law to predict the motion of the object. You could have done this lab using the energy principle, but I chose to do it with Newton's second law. Another key factor in this lab will be the coefficient of restitution, which is the ratio of the final velocity of inertia to the initial velocity between the two objects after their collisions, as shown in the top of the animation. You can also find this by taking the square root of the ratio of the height of each ball at each time it is dropped. Some initial information about the ball is that its mass was 0.0412 kilograms. The initial position vector is given in meters and the initial velocity vector was 0 joules per second. So here's the data from Tracker. You can see that I dropped the ball from an observed height and then tracked its motion as it fell and bounced multiple times. The x and y data is displayed on the right. So the fundamental principle at work here is Newton's second law, where force equals mass times acceleration. F net is just going to equal the force of gravity in this situation because we will be ignoring drag force. The two change in position and change in velocities were both informed by Newton's second law and are defined by these equations. For my code, I initialized it by setting the ball's mass equal to that of the ball I dropped. The ball's position vector and the ball's velocity vector are those of the initial values. And then the CR value, which we'll get into more later in the lab, was found to be 0.75. And so in our while loop, what I did was I added an if statement to calculate du, to calculate the ball's bounce. And so each time the ball's velocity, our ball's position equaled 0, which is when it hits the floor. I multiplied that by the CR value and negated the velocity. So then we had the initial kinetic energy and initial gravitational energy. F grab equals the vector of the ball's mass times g negative. Gf net is just equal to F grab, and then the ball's velocity in the ball's position equations are dictated by Newton's second law. And so I coded it so that we could put in a CSV file of the data extracted from Tracker, and we'll compare that data with the computational model, which we will see in this slide. The blue ball is the computational model, and the red ball is the observed data extracted from Tracker. We imported the file and then let the code run. And you can see that as the balls bounce, they achieve a height that we can then analyze to calculate CR. I found CR to best fit 0.75, and you can also fact check this by taking the square root of the height of the ratio of the first bounce to the second bounce and so on, as I said earlier. And you can see that the second bounce achieves about roughly half of the height of where it was dropped from, and the square root of 0.5 is equal to 0.7, 0.07, which will then give you our CR value. So what does the coefficient of restitution or say about our collision? The coefficient of restitution will depend on what two objects are interacting with one another and how they will store energy. When a soft object strikes a harder object, most of the energy available for the post-collision velocity will be stored in the soft object. The coefficient of restitution will therefore depend on how efficient the soft object is at storing energy, compression without losing it, or plastic deformation, for example. A rubber band ball will bounce better off of concrete than a metal ball, because the coefficient of restitution of the metal on metal is a lot higher than that of rubber on rubber, because the sum of the energy and rubber is lost to heat when it is compressed. In conclusion, this lab is a simple way for us to understand an inelastic collision and make better judgments about how two objects will interact after our collision. Thank you.